All right, this is more than meets the eye. Let's go ahead and do some transformations today, 2.6. Here we have y equals x squared. We will call that the parent graph. The parent graph. We all know that x squared is just a parabola. It's a nice happy parabola with the vertex as 0, 0. Here now for today's lesson, we're just going to go ahead and transform it. Basically, we're going to move it around using its original parent equation, y equals x squared. What do you guys think will happen if I put a negative in front? Oh. It will go like this. Oh, that's bad. I mean, it's drawn pretty badly, but in mathematics, we say that the graph is reflected across the x-axis. So basically, here's the x-axis. It is reflected across the x-axis. Pretend that's drawn perfectly. I'm trying to use a mouse to draw it, so that's why. So when we put a negative in front of the parent graph, it is reflected across the x-axis. What happens if we put the negative inside the parentheses so that it goes before the square? The guess would be it's also reflected, but this time it's reflected across the y-axis. So here's the y-axis. If you reflect it across the y-axis, it actually looks exactly the same. So there is a transformation, you just can't see it in this particular example because it just loops around. So when it's outside the parentheses, it's reflected across the x-axis. When it's inside the parentheses, it's reflected across the y-axis. What happens if I put a +3 at the end? Or sometimes I could put a +3 in the front, it doesn't matter. The +3 will actually move the graph up 3 units. So instead of starting at 0, 0, it's going to start right at 0, 3, and it's going to look the same. It's just parabola. It's the same exact parabola, but it's just shifted up 3 units. What happens when it's x squared minus 7? Now a lot of people think, oh, that has something to do with shifting 7 units, but since it's minus, it might reflect it, might flip it upside down, but that is not the case. It is just shifted 7 units down. So take the vertex, shift it 7 units down, and then it's still, it still opens up. It's supposed to be the same width, just in case you're wondering. All right, so the number that is added or subtracted to the parent just moves it up or down, depending on if it's plus or minus. Let's take a look at this. What happens when I put the +3 inside the parentheses? Hopefully you guessed that it shifts to the right or to the left, and that is going to be correct. In this case, that +3 in the parentheses shifts it to the left 3 units. So instead of 0, 0, it is at 0, -3, and then it's the same graph. It almost looks good, but yes, that +3 on the inside just shifts it to the left 3. What about the what about the minus 7? X minus 7. I hope your guess was it shifts it to the right 7. And it still goes up just like that. All right, so know the differences when something is happening outside, it means it's going to go up or down, but when something is happening on the inside of the parentheses, it goes left or right. So know the differences. What happens if I just put a 3 in the front of the x and you're multiplying it by 3? What guesses you have? Oh, I did that on accident. Pretend that didn't come up yet. This times 3. If you guessed that it got skinnier, you would be correct. It would be the same starting point, but it's just skinnier. The mathematical term for being skinny is vertically stretched. If you think of it as a rubber band and you take it and then you vertically stretch it, what happens to the rubber band? It becomes really skinny. And so the mathematical term for skinny is vertically stretched. And then I already the next example came up too. What happens when it's a fraction or when you divide by a number? Hopefully your guess would be that it would get wider. So it'd be wider. And the same thing, the mathematical term, if you take a rubber band and then you squish it, push it down, the rubber band would become wider. So the mathematical term for something getting wider is vertically compressed. You're squishing it down, so then the graph gets wider. And so it would look something like this. That means symmetric. I apologize again for my rough freehand drawing, but there it is. And a good way to remember which way is skinny, which way is wide, is you can kind of think of the numbers, the coefficients in the front as the slope. This is 3 over 1. This first one is 3 over 1, so it's up 3 over 1, up 3 over 1, up 3 over 1. Both ways, up 3 over 1, up 3 over 1, up 3 over 1. So it's a little bit skinnier. And then the other one, I'll change colors to blue. The 1 over 3 is up 1 over 3, up 1 over 3, up 1 over 3 both ways. And you can see that that's way wider. Okay, so that's a good way to remember if it gets skinnier or if it gets wider. Kind of think of it as a slope. It's not quite the slope, just because these are parabolas and they have curves on them. So there's not really a slope, but if you think about it that way, it helps to remember which one's skinnier and which one's wider. I don't know. I think I left this one on the next slide. Hopefully it'll show up on the next slide. Oh, it doesn't. I'll pause this and see if that helps. All right, so that last example that my face was covering, I rewrote it up here so that my face doesn't cover it anymore. But you have to look at the graph, look at the equation and see what types of transformation, what happened to our parent. How did it move? How did it change? All right, and we can look at each individual thing at a time. The first thing we can look at is this negative. Remember, that means it's reflected across the x-axis. How about this 2? Vertically stretched. It got kind of skinnier. How about this 5? Inside the parentheses, moves to the left 5 units. And then finally, this -9 means it goes down 9. So that's kind of cool. Looking at that super complicated equation, you can tell exactly what it looks like and how it goes. You have to make it a sad face. You have to make it a little bit skinnier. Then you have to move it to the left, to the left 5 units, and then you have to move it down 9 units. So kind of cool just to look at the equation and say exactly what happened to it. Not bad at all. This also applies with square root equations, like the square root. The parent graph, I forgot to write it, is y equals the square root of x. That would be the original equation. Now, what do you think happens when I put a +4 on the inside of the root? It just moves it 4 units to the left. What if the +4 is on the outside? 4 units up. And then what if I put a 1/4 multiplying it? It's just vertically compressed by a factor of 1/4. Is that what you say? Vertically compressed. You squish it, it gets wider. All right, so the same rules apply to square root equations. Kind of cool. Going backwards, what if I tell you what happens and you have to come up with the equation or the function? Here's the parent, f of x is equal to x squared. What if I told you to move that parent up 7 units and then vertically stretch it by a factor of 5? How would you write that equation? This would be how. So the up 7 comes from here, and then the stretched comes from there. Okay? All right, and not only does it work with square equations and square root equations, it works with absolute value equations as well. What if I asked you to vertically compress this equation by a factor of 1/7 and then move it 2 units to the right? Where am I going to put the 1/7 and where am I going to put the 2? There it is, the 1/7 in the front multiplying, and then a 2, the -2 inside the absolute value bar. That makes it left or right. All right, so hopefully you're catching on to some of the patterns. On the homework, you're also going to get some tables. So obviously when we graph tables, we use the t-table, plot points, and we come up with a graph. So this is going to be part of the homework, but you're not going to be asked to graph it. You're just going to be asked to come up with a new t-table based on the directions that they ask you to translate. All right, so here's our original table. How do we move this graph 5 units down, what do you think you have to do? 5 units down, that's in the y direction. So you're only going to fix the y's by subtracting 5 from each of those numbers. There it is. A 3 minus 5, 0 minus 5, negative 1 minus 5, 0 minus 5, and then I know you can't see it because my face is in the way, but that 3 minus 5 gives you a negative 2. All right, so if you're asked to move something up or down, that's what you do to the y value only. Okay? All right, this is our last slide for the day. Same thing, what if I asked you to move it from this function into this function? All right, so if you notice, the original has a 5x. There's our 5x. What else happens? We have a 1/7 that's multiplied. So when you multiply the graph by 1/7, it just makes it wider. So vertically compressed. I know you guys need to write the whole word. It's difficult for me to write it with the mouse. That's why I just went VC, but vertically compressed. And this -3 says that it goes down 3 units. All right, so we can do it with equations, we can do it with t-tables, and we can also do it with 2 different functions, f of x and g of x. All right, that is all we have for today. Go ahead and try the homework.